So hey, let's talk more about the chain rule for derivatives. I want to pick up at section 3 of Note Packet 20, and we're talking about the chain rule or the composition rule. And again, I like the composition rule as a name for it because we're working on compositions of functions. So I wanted to give you some advice for doing these problems. I think one prominent piece of advice that I wanted to highlight for you is to work on one level of a composition at a time, and that all others stay the same. So, for example, if I'm working on e to the sine of x squared, I've got a couple of different levels. I've got an e to the, I've got a sine, and then I have x squared. So I have 1, 2, 3 levels of things to pay attention to. And when I take the derivative, I focus on, at first, just the e to the part of it, and the other stuff stays the same. And then I just work the chain out that way. Let me put a prime right there and then take this derivative. This derivative is equal to, okay, so I'm going to do the 3 levels in sequence. At first I have e to the, and the derivative of e to the is e to the. Okay, and so that was level 1. Level 2, and I take the product of these things for each level. So now I chain out the derivative of the sine of x squared. And I'm just going to leave the x squared part the same. I'm just working on one level at a time. So I'm just going to take the derivative of sine, and the derivative of sine is cosine, and then the stuff on the inside stays the same. And now I'm ready to work on the derivative of the next level, and the derivative of x squared is 2x. And that's kind of a way to pay attention to which level of composition we're working on at a time, and leaving all others the same as I work through the composition or the chain of functions. I have found that there is a couple of distinct perspectives in terms of the way that we do these. So inside out, I'm gonna write the function x cubed plus 2x plus 1 to the 5th in 2 different ways. X cubed plus 2x plus or no, that's supposed to be minus, isn't it? So that's minus 1. Wow, that's really quite large. So minus 1. Okay. To the 5th. As I work through my levels of composition one at a time, all others staying the same, I'll highlight here. So I've got 1 here, and I've got 1, the something to the 5th. And so the inside out perspective is going to focus on the innermost function first. Okay. And the outer side is going to do the outermost first. Let's do the inside out one first. So I'm going to focus on the inside function, and that's this x cubed plus 2x minus 1. So when I take the derivative of this expression, so let me surround that with a pair of parentheses and then prime it. So I'll have 3x squared plus 2, and then I need to take the derivative of the outside thing, and that's going to be something to the 5th power, and so I have 5 times that something to the 4th power. Okay? And so I write them from innermost to outermost. And the order of these doesn't actually matter. Because A times B is equal to B times A. over the real numbers as well as the complex numbers. So so the order doesn't matter. But as far as paying attention to doing chain rule problems, focusing on the inside and going out one level at a time is one perspective. So this is a perspective. And you may find that one of these two perspectives works better for you. So this is another perspective. So I'm going to focus on the outermost function first when I take the derivative of this expression, and I've got something to the fifth power. The derivative of something to the fifth power is 5 times that something to the fourth power, and now I need to chain out the derivative of the inside, and so I'll multiply by the derivative of the inside, 3x squared plus 2, and then there's nothing else inside, and so I'm done. This is if you watch me do chain rule derivatives, this is what I typically do. Not always, but usually. I'm not perfectly consistent, and I think that's okay. This last statement here, pay attention to implicit functions of time and space, is a note leading forward to the next lecture. That is to say, as a preview, if I'm taking the derivative with respect to x of some expression f of y, that's like, where's the x? Y is implicitly a function of x. How do you know that? Well, you would know that because you somehow understood it. See the next lecture. And so we have to be sure to chain out the derivatives of y with respect to x in order to get there. And that'll make more sense, again, when we do section 3.8. Okay, I'm going to turn the page. We give you these rules for taking derivatives of expressions, of various basic functions, and this one right here, this is for the basic e to the x. This is the basic. This is what I think of as the basic rule. This is useful for e to the x, but not e to the sine of x, in a sense, unless you remember that you have to here chain out the derivative of the inside thing. So the second one here, this is the general rule. What makes it so general? Well, I've got not just x, but f of x. Okay? Well, the derivative, okay, so using the chain rule, it tells us how to take derivatives of compositions, and it tells us that we have to chain out the derivative of the inside thing. So I've got here f of x is the inside function. And I need to chain out the derivative of the inside function when I use the chain rule. I put formulas on this page for you that express the basic rule and the general rule um, for the exponential rule that says that e to the x prime is equal to e to the x, or that x to the n prime is equal to n times x to the n minus 1. So those are the basic rules. And I wrote those rules a couple of different ways for you. This one right here was with differential operators and f's. And this one right here, I used square because square is just whatever the inside thing is. I like using square because we don't get attached to a particular name for it. We can see that it's like completely generic. And then kind of the ones that I really like to focus on are the ones with the primes. So I really like this way of writing it because it's kind of minimal in terms of the number of symbols. We don't get lost in a sea of differential operators. I'm taking e to the square, e to the box prime is e to the box, and then I have to chain out the derivative of the inside function right here. So in terms of the power rule, I would have something to the nth power, and when I take the derivative of that expression, my n comes down front, and I reduce that power by 1. The thing on the inside stays the same. I still have a square, and then I have to chain out the derivative of the inside. So when I say chain it out, I mean take whatever was on the inside and then take the derivative and multiply it on the outside. Yeah. So we keep giving you statements like sine of x prime is equal to cosine of x. And then from this, you're supposed to know, chain rule. Okay? So these simple expressions like this, they're all like, okay, that's just for what if the thing inside here is just plain x. And in any other case, you've got to take that other thing prime on the outside. So the basic formulas do for you. They do capture everything if you're willing to remember that if there's something more fancy than x on the inside, you have to chain out the derivative on the outside. So I'm going to change pages. So in order to really drive that point home, I put up the derivatives of the trigonometric functions for you. And I started with just squares. Okay, so I started with just squares, in all of these cases, I've got the basic formula. So the derivative of sine is cosine. The derivative of cosine is minus sine. I've got my squares to indicate that it doesn't matter what's on the inside there. That's always going to stay the same in all of these places. So wherever we saw square on the left-hand side, we're still going to see a square on the right-hand side. And then in all of those cases, we always multiply by whatever was on the inside, and we take the derivative of it. Okay? So this, always has a square prime after it. So in some sense, it's like, well, yeah, okay, they all have a square prime. So, it seems like just a lot to remember. And that's why we just give you the basic formulas, and then you just have to remember, I chain it out on the outside. So in order to really drive home that it doesn't matter what's on the inside there, I repeated the same formulas with hearts. because I mean, who doesn't need a little extra love in the world of mathematics, especially right now? Like spades are fun. It's also cool if we name it a traditional name for a function. So f, and I omitted the of x or of whatever it happens to be. And in the case that we have here the inside function, which would be called, say, square or heart or the spade, which is really hard to draw because I've never drawn one before, or f, then I just get right here, here's f of x, and when I take its derivative, this thing right here is just x prime, and multiplying by 1 doesn't do anything. It's the multiplicative identity. And so we recover the simple formulas that we give you up front. These are actually a special case where f of x is equal to just the identity function. So these two boxes, box A and box B, they say the same thing. It's just that the one on the left is explicit about the chain rule. And this one over here on the right hand side, box B, leaves the chain rule implicit. And the user has to remember. That the chain rule is in effect. So which way you think that you want to go, whether box A is the way that you think about things, and you really want to see, oh, I multiply by the derivative of the inside function, or whether box B is good for you and you can remember, oh, if it's anything more complicated than just plain x, then over here or out front, multiplication doesn't matter, it commutes. You need to multiply by the derivative of the inside thing. They're both good, and there's value for doing both. I'm going to turn the page. Let's do some more examples. So let's start with one on the top left here. E to the 1 plus sine of x. How about we call this? Well, I don't feel a particular name to. I don't feel a particular motivation to name them, but we could call that one f. That way I can write f prime equals. So what I'm going to do is I'm going to recognize that the top level. I'm an outside in person when I do the chain rule. So here the outer function is e to the, and the derivative of e to the is e to the. So f prime is e to the, and then I need to take the derivative of the inside function and multiply it down here. And the derivative of 1 plus sine of x is cosine of x. And there's a hidden derivative of 1 is 0 that I didn't bother to write. Let's do sine cubed. Let's call it g. And let's go g prime. So it kind of looks like, as we approach this, I'm still taking the outside in approach. Because that's what my brain likes to do. So I'm thinking, what's the outermost thing? Now, these kinds of functions like this can be deceiving because it looks like the outermost function is sine, but it's not. The outermost thing is to the third, because this is equal to sine of x cubed. So when I take this derivative, I'm going to take the derivative of the outside thing first. And so I'm going to have 3 times sine of x squared. Leaving the inside part is untouched, right? Wow, that yellow is not terribly legible. What if I use like light blue? So the inside remains unchanged, and then I need to chain out the derivative of the inside times cosine of x. And if we wanted to write it more similar to the original function, maybe I would call this 3 sine squared x cosine of x. Okay, let's go down to the sine of sine. These functions are kind of fun to do. Let's name it. Let's call it h. And let's write down what h prime is. The outermost function in this case is sine. So when I take the derivative, I'm going to do the outermost function. I've got, the derivative of the outermost function. The outermost function is sine. So the derivative of sine is cosine. And then the inner part stays the same. And then I'm going to take the inside of that one and I'm going to chain out the derivative of the inside. And I'm going to have cosine of x. Now, I don't really have any way to simplify this expression per se. I think that's about as simple as we're going to make that one. Let's do one more. Let's call this function k. The outermost function here is the division. So the outermost thing that we're doing is taking a quotient. So when I write what k prime is equal to, I'm going to do the quotient first. And so I've got the top and I've got the bottom, or what we were calling high and low. So I go, when I do k prime, I do, right, remember I go, for quotient, I go low, d high minus high, d low, draw a line, and square below. So let's go ahead and do that. Let's do low, sine of pi x times d high minus high, careful with those parens, times d low, and now we're going to have a chain rule. So we need to figure out right here what sine of pi x prime is equal to. So let's work that out over here. Sine of pi x prime is equal to, the outermost function is sine. The derivative of function of sine is cosine, with the inside staying the same, and then I chain out the derivative of the inside times pi. And we often will take these multiplicative things right here and move them to the front, so that way I don't get confused, right? Because this multiplication by pi, this multiplication by pi is not inside of the cosine. So I would write that as pi times cosine of pi x. So now we're ready to put that into place right here. So now let's draw a line and square below. Low d high. Let's double check our work first. Low d high minus high d low. Okay, draw a line and square below. No problem. Sine squared of pi times x. And I see no available ways to simplify this expression whatsoever. Beware that I know students see a sine of pi x right here, and they'll see one right here, and they want to cancel those. But because there's no sine of pi x in this term right here, this bottom one of these does not cancel. So don't cancel. Okay. There's a pitfall there. Okay. Those are some good problems. Let's turn the page. Ooh, I really like this one. This one's good. Word problems are all over the place in terms of calculus. It really is a descriptive language. And so our real goal is to be able to solve real problems where we don't tell you what the functions are. There's just a situation and we have to figure it out. Okay, so let's just read the problem aloud. A spherical balloon is radius r, and that radius is increasing at a rate of 3 centimeters a second. At what rate is the volume V of the balloon increasing when the radius is 10 centimeters? I'm going to draw a picture. I think that's the right place to start. So let's draw a sphere. There's a spherical balloon. We're going to neglect the hole in which we're injecting the air. Let's go ahead and label the radius r. At what rate is the volume V of the balloon increasing when r is equal to 10? Okay, well, let's see here. So we should probably go ahead and write down what V is as an expression of r. The volume is determined by the radius, and that's 4/3, that's a 3, I swear, 4/3 times pi r cubed. And we've got a rate where the volume is increasing, right? So we're thinking about V prime. That is to say, we're thinking about how the volume changes as a function of the radius when the radius is changing. So this expression dv over dr is asking the question, how does the volume increase or change as a function of radius? Except that there's an additional thing going on here. I don't think that this completely describes what we're doing. I think we're actually interested in dv dt because there's a time rate of change here. But v is a function of r, right? V is a function of r. Oh, but r is equal to r of t. R is a function of time. The radius is a function of time, right? Look. The radius is increasing at a rate of 3 centimeters per second. So we need a chain rule here in order to solve this problem. dv dt is equal to dv dr times dr dt. Ah, okay. This is because of the chain rule. Ultimately, the volume is set by the radius, but the radius is changing with respect to time. And so the rate at which the volume is changing with respect to time is the product of how the volume changes with respect to radius and how the radius changes with respect to time. So dv dr is equal to, well, I'm going to take the derivative of v with respect to r. Then we're going to get 4 times pi r squared. That is dv dr. And then I need to multiply it by dr dt. Oh, 3 centimeters a second. And it looks like we're not quite done, and we're not, because we should get a number. This is particularly when r is equal to 10 centimeters. So I need to make r be equal to 10 centimeters. So we need to substitute in r equals 10 to find out the rate that it's changing, the volume is changing when the radius is 10. Because the size of the balloon affects how fast the volume is changing. So this is equal to 4 times pi times 10 squared times 3 is equal to 12 times pi times 100, which is equal to 1200 pi centimeters cubed per second. So somewhere on the order of 3 liters per second. That's really fast. In my experience, 3 liters is a lot, and that's a lot to do in a second. So I think I should annotate this. I want to go back and particularly suggest that dv/dr is how the volume changes with respect to the radius, but the critical realization to make right here is that r equals r of t, and dr dt is equal to 3 centimeters per second. So ultimately we were interested in the time increase, the time rate of increase of my volume. And the way I got there was by doing the chain rule. Let's turn the page. Let's do a few more problems here. Let's start with y is equal to sine of x squared. And let's figure what y prime is equal to. Go ahead and pause the video and give this one a try. And then unpause it when you're ready to see me work through it, okay? Okay, let's see if you get the same thing that I got. I'm totally an outside-in person. And if you're an inside-out person, then yours will, you'll get the same function, but you'll get it in a different order. So on the outside, I've got my sine function. The derivative of sine is cosine, and I leave the argument the same. And then I've got to chain out the derivative of the inside, and I get 2x. And we very often like to take those factors and leave them up front. And so I would probably write this as 2x times cosine of x squared. Let's do the next one. I see y equals z plus 1 to the 4th times 2z minus 1 cubed. Let's take y prime. Go ahead and pause the video and give it a try. And then when you're ready, unpause the video and see me work through this derivative. Okay, so I think the first thing that I want to point out is that there's a times right there. So I feel like the outermost thing that's going on right here is a product. So the first thing that we're going to do when we do this is the product rule. And I'm going to do it by doing like prime placeholders to indicate the derivatives that I need to take as I do this. I'm not going to do it all in one line because I feel like I could easily skip steps if I start doing that. So let's do this as z plus 1 to the 4th prime times 2z minus 1 cubed plus, careful on those parens there, Silviana, plus z plus 1 to the 4th times 2z minus 1 cubed prime. So I've got the derivative of the first times the second plus the first times the derivative of the second. And now I'm ready to do those primes. So let's go ahead and do that. I've got a to the 4th in the z plus 1 to the 4th. So that's going to be 4z plus 1 to the 3rd. And now I'm going to go ahead and chain out the derivative of the inside there. And that's the derivative is 1. Second is unchanged, 2z minus 1 cubed plus z plus 1 to the 4th, fine, unchanged. And now we've got to take the derivative of this next part. And the outermost thing is to the 3rd. And so I'm going to have times 3z minus 2z minus 1 squared. And now I've got to chain out the derivative of the inside times 2. I think we can do a little bit of cleanup on this. I'm going to let this 2 and this 3 merge together and become a 6 and move it to the front. I'm going to let this 4 and this 1 merge together, and then I'm going to move them to the front. And so I'll just write this as 4z plus 1 cubed times 2z minus 1 cubed plus z plus 1 to the 4th with a 6 all the way out front times 2z minus 1 squared. Yeah. Seems good. Let's do one more problem here on page 8. So let's consider y equals the square root of a quotient. Go ahead and pause the video and give this a try. If you want a hint, moving forward, rewrite that square root using a 1/2 power. Okay, so I'm going to go ahead and rewrite this expression as z plus 1 over z minus 1 to the 1/2. So that that facilitates me when I take y prime. The outermost thing is that to the 1/2. Okay, so when I take the derivative of this expression, I'm going to deal with that that power rule. So I'm going to have a 1/2 times z plus 1 over z minus 1 to the minus 1/2. And now I'm going to take the inside and I'm going to chain it out. And I'll go ahead and write that as a placeholder, and then we'll do that on the next line. So it's going to be z plus 1 over z minus 1 prime. So I'll just kind of repeat these. Plus 1, z minus 1, minus 1/2. times, and now I'm going to do our friend the quotient rule on this quotient. So we'll go low, d high, minus high, d low, draw a line, and square below. I don't feel like those times ones are really doing a whole lot for me. So let me go ahead and erase those. And I think that we're done. There is a temptation in terms of these. So those two places right there, people are going to be tempted to cancel, but don't cancel because you don't have one right here. So if you try to cancel, you can only cancel out of the bottom here if everything on top has one, or else the cancellation's illegal and what you get is not equal. So just be careful about that. All right. Let's go ahead and move to the very last page right here. Let's do one more of these derivatives, and then we can kind of call it good. I'm not going to do this last one. So let's just focus our attention on this one here. If you feel like you're already mastered on computing derivatives with the chain rule, by all means, stop and move on and do something else. But in the meantime, let's go ahead and do this one. So we want to compute y prime. It might be helpful. I feel like it's helpful when dealing with square roots to rewrite things so that I have the power explicitly. 1 plus x squared plus 1 1/2, all to the 1/2. So I'm totally an outside-in person. The outermost thing that I'm doing is that 1/2. And so when I take the derivative, I'm going to use the power rule. And I'm going to have 1/2 of the stuff on the inside stays the same. So stuff on the inside stayed the same. And now I go to the minus 1/2. Now we need to chain out the derivative of the inside. The derivative of the inside is 0 plus 1/2, because I've got this next level of chainedness, and the outermost thing there is a half, so 1/2 times x squared plus 1 to the minus 1/2. And when I take that derivative, now I've got another thing on the inside, and I need to chain it out. And that's still on the inside of the paren that we're inside of. So let me highlight that. So that paren is the same as that paren. And the derivative of x squared plus 1 is 2x. This could definitely be simpler. So let's look for available simplifications. I see a simplification. I've got this half here and this 2 here. A half times 2 is 1. So that seems good. And let's drop that. So let's drop that plus 0 and write this as a half of 1 plus x squared plus 1 to the minus a half times x x squared plus 1 to the minus half times x. Okay. So I feel like methodical application of the rule of the chain rule is what's going to get you there. As you can see, I keep doing these problems with an approach that starts with the outermost thing and just works one level at a time. So going back to the advice from page 3, I gave you some advice. It was kind of where I started this out. I think you should work on one level of composition at a time, and all others stay the same. And you should. So I keep taking the outside in perspective as I do this. So that was this one. That's this perspective. This is what I do. So this is what Professor does. Yeah. So just like find the outermost thing and work on it and leave everything on the inside the same and then chain out. Chain it out. It's a whole lot of chaining it out. Well, that's it for this session together. Good luck, and I wish you all the best as you work through the chain rule. Thank you. Bye.